All right, let's work through these practice problems that I put online. Um, Here's the first problem. It says a 16-centimeter diameter circular loop of wire is placed in a 0.50 Tesla magnetic field. When the plane of the loop is perpendicular to the field line, so let's see if we can draw what that would look like. So we'll let the magnetic field be uniform and point to the right. It's an easy way to draw it. And then we will have this loop of wire, circular loop of wire, that is perpendicular to it. If the loop is perpendicular, it means the normal to the loop is parallel with B. So N is parallel to B, whereas the plane is actually perpendicular to B. Just what is the magnetic flux through the loop? Well, our formula for magnetic flux is BA cosine phi. And in this case, phi, remember, is the angle between the normal and B. If they are parallel, it is 0. So cosine phi is just 1. So it's just the product of the magnetic field and the area. Now we have to be careful about the area. I need the area to be in square meters. It tells me that the diameter is 16 centimeters. So that tells me the radius is 8 centimeters. Or if we're going to do it, 0.080 meters. We want to keep our two significant digits. So area of a circle is pi r squared. So we have this 0.50 Tesla times an area of pi times 0.080 meters squared. Now it's just a calculator question. 0.5 times, whoops, turn the calculator on. 0.5 times pi times r squared. And it comes out to be 0.010, oh, not Tesla. Erase that real quick. That should be Webers. Or if we multiply that by 1,000, we could say that it was 10 milliwebers. But they didn't ask us to do that, so really, there's our answer. That is the flux if it's perpendicular. Okay, so we got the answer to the first part. All right, part B says, the plane of the loop is rotated until it makes a 35-degree angle with the field line. So we've got to kind of change our picture here. Let's go back, let's draw our field lines. We'll keep our field lines pointing to the right. And now we're going to make our loop have a 35-degree. But notice it's the plane of the loop makes a 35-degree angle. So 35 degrees, let's see, something like this. That angle looks about 35 degrees. So if this angle is 35 degrees, the normal is going to make an angle of about 90 minus. Remember, the normal is perpendicular. So in this case, the answer to the second question is phi is a 55-degree angle. And then it says, what is the magnetic flux through the loop at this angle? Obviously, we're going to be reduced, and we're basically going to be just reduced by cosine 55. The BA is going to stay the same. We could write it all out again if we want to, 0.50 pi r squared times cosine 55 degrees. I have no idea what that window is up there. So 0.50 times pi r squared times cosine of 55. And it causes it to fall to roughly 0.0058. So down quite a bit Webers. All right, so that takes care of the first problem. First problem is really just about, do we remember how to calculate magnetic flux? So let's move on to our second problem, and I'm just going to try to see if we can move all of this. Whoops. Move all of that off the page. Okay, so it says a 40 centimeter solenoid, 1.35 centimeters in diameter, is to produce a magnetic field of 0.385 Tesla at its center. How much current should the solenoid carry if it has 765 turns of wire? So we have to go back and brush up. How does a solenoid work? A solenoid has a magnetic field equal to mu naught n I, and that's on your formula chart. And I did update the formula chart. You may want to take a print your fresh copy. I put a few more pieces of information on it. N is equal to the number of turns in per meter. Okay, so this formula that we're using for a solenoid, remember, a solenoid is a long coil. It's valid when the diameter is relatively small compared to the length. So since we are 40 centimeters long but only 1.35, we don't need, there is another formula that's used sometimes for coils. If you have just a few turns, but for a long solenoid, this is our best formula. So we want the magnetic field to be 0.385 Tesla, so we'll put that in for B. Mu naught is that constant 4 pi times 10 to the negative 7. N is what we really don't know. We do know N. Sorry, I stand corrected. N is the number of turns per meter. There are 765 turns, and 40 centimeters is 0.40 meters. So that's our lowercase n. So we just have to solve for the current. How much current is it going to take to give us that magnitude of magnetic field? So again, now we're ready for a calculator. 0.385, I divide it by mu naught. So I'm going to divide by that 4 pi times 10 to the negative 7. And then I'm going to, of course, multiply by the reciprocal of that 765 of 0.4. So times 0.4 divided by 765. So after pressing all the buttons, I see it's going to take a lot of current to get that magnitude of magnetic field the current's going to have to be 160 amps. So that is the answer to part A. So how much current? 160 amps. That is a lot of current. All right, part B says if a single circular loop of wire with a radius of 1 centimeter is placed inside the solenoid as shown, what is the magnitude of flux through the loop? Well, we just did a flux. Okay, inside of a solenoid, you have a uniform B, and they tell us in the problem that we want that uniform B to be 0.385 Tesla. We don't know whether that uniform magnetic field is pointing into the page or out of the page, but they didn't ask us to worry about that. We just need to know what B is. So for part B, then if we're going to calculate flux, it is simply going to be B times A. Again, the plane of that inner circle is clearly perpendicular to the direction of the magnetic field. A magnetic field inside of a solenoid, it looks like this. Those lines are fairly uniform inside. You get a nice uniform magnetic field. So just B times A. So we have 0.385 Tesla. The area is a circle, so pi r squared. The radius is 1 centimeter, so 0.01 squared. And that's going to tell us how much flux we have. So 0.385 times pi times 0.01 squared. So I get the flux is 1.2. How many significant digits? Be very careful. So 1.21 times 10 to the negative 4 Webers. All right, so far so good. Let's look at part C. If the current is reduced to half of its original amount in a period of 4 milliseconds, what is the induced EMF and induced current in the loop? The resistance of the loop is 2 ohms. Make sure we all really do understand what's going on here. This is the solenoid if we're looking at it from one end. And this is the loop inside. Okay. If we have a magnetic flux going through that loop and we suddenly change it, we're going to have an induced EMF. Let's erase and make some room. So, okay, so now we're going to be on part C. What do we get here? 1.21 times 10 to the negative 4 Webers. All right, if the current's reduced to half in a period of 4 milliseconds, what's going to happen? Well, if you reduce the current, look what happens to your magnetic field. If I cut the current in half, B falls to half. All right, what's that do to the flux? The flux, which is BA, is also falls to half. Okay. Induced EMF is the absolute value of the change in flux divided by the change in time. In this case, we went from a flux that was 1.21 times 10 to the negative 4 to an amount that was half of that. If I do 1.21 times 10 to the negative 4 and I divide by 2, I'm going to get a flux that's 6.05 times 10 to the negative 5. That's how much the flux changed. And it all happened in 4 milliseconds. Oops, milli is 3. Sorry about that. When you're taking the test, do pay good attention to things like milliseconds. Make sure that you're catching those details. So the flux basically was cut in half. It went from 1.21 times 10 to the negative 4 down to 6.05 times 10 to the negative 5th. It took 4 milliseconds. So if I do this and I divide by 4 times 10 to the negative 3, I get that the induced EMF is very small, not too surprising, is 0.0151 volts. If we keep our 3 significant digits, that's our induced EMF. To get the last answer, I use Ohm's law. I know that the current is equal to the voltage divided by the resistance. So 0.0151 volts divided by 2 ohms. Just going to cut it in half. And I get 0.00756. If I multiply that times 1,000, I could change that to milliamps. It's 7.56 milliamps. Now, it's going to be a very small current, and it's only going to have that current for the length for that 4 milliseconds. Once that magnetic field is stable and it's no longer changing, then there's no longer an induced EMF. All right, so that's our second problem. Let's do our third problem, and then I think we will stop this video, and I'll do the other 3 problems on a separate one. So these are our chapter 21 problems. And okay, I just want to make room just for the problems I'm working. It says a cell phone charger contains a transformer that reduces 120 volts to 5 volts. The second coil has 30 turns and supplies 700 milliamps to the cell phone battery. First question, how many turns are in the primary? Well, thank goodness, transformers are easy. The ratio of whoops, not sure why that went up there. The ratio of turns is the same as the ratio of the voltages. So in this particular situation, the secondary coil has 30 turns. We don't know how many are in the primary. I don't know how to make those stop. The secondary voltage is 5 volts. The primary voltage was 120 volts. If I'm going to solve a proportion, I'm just going to cross multiply and solve. 30 times 120 divided by 5. And I see that the number of turns in the primary is 720 turns. So very straightforward question there. Question B says, how much current is in the primary coil? Well, we know that the power in the primary is V1I1, And in an ideal transformer, that is equal to the power in the secondary. In an ideal transformer, we have no power loss. So we know that the input was 120 volts. I don't know the current. I know the output was 5 volts. And the output current, it says it supplies 700 milliamps to the cell phone battery. So 700, I can leave this in milliamps. It will just mean that my answer will be in milliamps. So I'm going to do 5 times 700 divided by 120. And I get that the input current is 29.2 milliamps. Question C says, how much power is transformed? Well, we've actually used the idea of power, but we haven't answered how much power we have in the whole thing. So I would say C, power is VI. I'm going to use V2I2 because both of those were given to me. So even if I messed up on one of the other parts, these were provided. So 5 volts times 700. I can't use milliamps. I have to do times 10 to the negative 3. Well, if I don't, I have to realize my answer would be in milliwatts. So I'm going to just do it in watts. 5 times 700 times 10 to the negative 3. And that's 3.5. And we really do only have 2 significant digits. So we will leave that like that. This one probably would have been more correct, right? 29 milliamps. All right, part D. What is the effective resistance felt in the primary coil? Basically, when you have a transformer, the actual wires in the coil of the primary may not have that much resistance, but we have what we call load resistance. That secondary coil and that cell phone charger that's connected to it, or that cell phone, they act like a resistor. But it's easy to calculate because we just say, look, V1 equals I1 R1, but R1 is not really the resistance of the primary so much as it's the resistance of what it thinks it's being put on. So we have 120 volts. It has a current of 29.2 milliamps. So 29 times 10, 29 times 10 to the negative 3 times R1, and sometimes they call this the effective, sometimes they call it the equivalent. So 120 divided by, and I'm going to put the 0.2 in there, 29.2 times 10 to the negative 3. And 2 significant digits, I get that that resistance is 4,100 ohms. All right, that takes care of the 3 practice problems from chapter 21. I'm going to do another video to go over the 3 practice problems from chapter 23.